In this video, I'm going to be discussing a concept called polarity. And polarity is basically a measurement of how electrons are shared in covalent bonds. So one thing I want to start right off with is that you only need to be concerned about polarity for covalent molecules, because since it talks about how electrons are shared, ionic compounds, which don't share electrons, remember there's a transfer of electrons, are irrelevant when it comes to polarity. Now, polarity is largely determined by a concept called electronegativity. And electronegativity is a measurement of an atom's ability to pull electrons towards itself. Pull electrons towards itself. Now that should not be confused with electron affinity. Remember we talked about electron affinity, and we talked about periodic trends. And electron affinity is a measurement of an atom's ability to pull an electron from another atom to ionize itself. Here we're talking about electrons that are already near the atom, such as in a shared chemical bond, and that atom's ability to just basically pull them in tightly towards itself. Okay? You can talk about first the polarity of individual bonds, and then you can use that to talk about polarity of a molecule as a whole. So looking at an individual bond, basically if the difference in electronegativity of the two atoms is large enough, then you have a polar bond. Now, the electronegativity of every atom is known. It can be found on some periodic tables, or you can look it up online. But basically the cutoff is 0.4. So what do I mean by that? Well, let's say we have a chemical bond between X and Y. If the electronegativity, and I want to say right now that electronegativity is on a scale of 4.0. The single most electronegative atom in the world is fluorine. So fluorine has an electronegativity of 4.0, and the lower you get, the less electronegative it is. So let's say we have an atom with an electronegativity of 3.0 and an electronegativity of 3.5 for the other one. The difference between the two is 0.5. So if it's greater than 0.4, that's a polar bond. So this would be a polar bond. If the difference between the two is less than 0.4, it's a non-polar bond. Now your textbook refers to it as a pure covalent bond, but it's more often referred to as non-polar. So what does that mean? Well, in a polar bond like this one right here, effectively what that means is that the more electronegative atom, Y in this case, is able to pull these electrons closer to itself. Think of it as if they're playing tug-of-war. And if the electronegativity difference is great enough, the higher number is like the stronger person in tug-of-war and is able to pull the center of that bond closer to itself. If it's non-polar, then basically they pull on the electrons evenly. So a non-polar bond is considered to be shared perfectly evenly, whereas a polar bond is not shared evenly. And this creates something called a dipole. So a dipole is a term you just get when you have a polar bond. It just means that there are two poles. Right? So the end of the dipole that has the more electronegative atom, that means again that more electrons are going to be handed out by that atom, which means that that end of the dipole behaves more negatively because there's more electrons there. Now there's two different notations for dipoles. You draw an arrow like this. So an arrow like this, the end that looks kind of like a plus sign represents the positive end of the dipole, which would be the less electronegative atom, and the end that looks like that is an arrowhead represents the negative end of the dipole. Or you could also give it this symbol. So almost looks like a little fancy D. With a positive sign, that means it's the positive end of the dipole. And you can put another one, negative end. That also represents what's called a partial positive and a partial negative charge because of the polarity. So that's now you won't always be given the actual electronegativity values. So I do want to give you a couple rules of thumb. Now, anything bonded to itself. So let's just say chlorine to chlorine, for instance. Anything bonded to itself, the electronegativity difference would obviously be 0. So that's always going to be nonpolar. Carbon and hydrogen bonded together is also nonpolar. If you have, however, carbon or hydrogen bonded to oxygen, nitrogen, fluorine, or chlorine, so one of these two bonded to any of these four, that would be polar. Now, of course, there are many other types of bonds you can have, but these are some very common ones that you'll see in your text and on assignments. So I want to basically give you these, so in case you aren't given the electronegativity values. So that's how you basically determine electronegativity in a single bond. But now let's talk about determining polarity in an entire molecule. So let's say we have a trigonal planar molecule right here, like this. If we make every one of these things around the central atom, if we make them all the exact same atom, well, let's say this is a polar bond between X and Y, because we'll still use this one right here, right? This basically means that even though, so all three bonds are polar, we'll draw their dipoles. Remember, the arrowhead always points towards the more negative end of the dipole. But think about it this way. If you have three people all pulling on something in the center, they're pulling in opposite directions, but all pulling with the exact same strength, is that thing going to go anywhere? No. It's going to stay perfectly centered. Similarly to this, if all of these have the exact same degree of polarity, and they're all pulling in opposite directions, effectively their polarities cancel out. So the individual bonds are still polar, but the molecule as a whole would be nonpolar. Now, basically, what that means is that for a molecule to be polar, for a molecule to be nonpolar, if it has any polar bonds, all of these bonds have to be the exact same type. So for instance, let's say we have, if we have carbon tetrafluoride, CF4. As I mentioned up here, a carbon-fluorine bond is polar, but all four of those are identical. So they all cancel out. Now, be careful. If I say we have C, F, and then H is right here, it looks like that should cancel out. It looks like these fluorines are exactly opposite of each other, so they should cancel out. And the carbon-hydrogen bonds are nonpolar, so that doesn't matter anyway. But don't forget, this is why you need to take into account because if you recall, even though we often will draw like this is a tetrahedral conformation, and in tetrahedral, there are no two bonds that are exactly opposite of each other. So, even though this looks like they're perfectly opposite and would cancel, they actually would not unless you have it like CF4 where they're all the same. If you have all nonpolar bonds and you have no lone pairs, you're just going to have a nonpolar molecule. So that would look something like this. Let's see, carbons surrounded by hydrogens. Those are all nonpolar bonds. There are no lone pairs. That's a nonpolar molecule. Now, talking about lone pairs. The only thing that can cancel out a lone pair is another lone pair on the exact same side of the molecule. Or, on the exact opposite side of the molecule. My apologies. So what do I mean by that? Well, let's look at water. Water, if you recall, I said is bent. So that means that these electrons are on the same side of the molecule here. So there's nothing that can cancel these out. Because Even with fluorine, if fluorine was here, that's the most electronegative atom in the world, but still not as strongly electronegative as actual electrons. So, if you have any kind of molecular geometry with lone pairs that are not exactly opposite each other, this will automatically be polar, no matter what. Now, an example of molecular geometry with lone pairs that can be polar is when I was talking about xenon tetrafluoride. So xenon tetrafluoride, if you recall from when I was drawing Lewis structures, this goes back to where I said that you had to, if you had 4 bonds, you had to put the lone pairs opposite each other. And hopefully, if you've watched the molecular geometry video at this point, you know that that's because this is now square planar, right? Where these are the 2 axial positions, and the fluorines are in the equatorial positions. So that means that these lone pairs are exactly opposite each other, so they do cancel each other out. And the fluorines also cancel each other out, so this is a non-polar molecule.